Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about quadrilaterals and circles. Let's jump right in, not with a quadrilateral, but with a triangle. Remember that we did in a previous video that a circle can always be circumscribed around a triangle. We talked a lot about this. We said, okay, we have the circumcircle, it has a radius. That circum is called the circumradius. You can find the circumcenter by looking at the perpendicular bisectors of the sides of the triangle. We had a lot of good information about how to create this circle, how to find information about this circle that can always be circumscribed around a triangle in this case. Now, our topic today is of course quadrilaterals. So we want to think about that a little bit more. And we actually have to take a step back and start with a simpler question. We want to start with this always question. Can a circle always be circumscribed around a quadrilateral? So if instead we have a quadrilateral, can you always draw a circle around this there? Now, if you think about it a little bit, try to picture it, the answer is fairly clearly going to be no. But let's talk a little bit here about how we can think about that and make that into an obvious statement. Well, let's again go back to our triangle. So let's suppose we have a triangle here. We know that there's always one unique circle that we can draw around a quadrilateral there. So we could think of this sides, some of these sides, for example, these ones that are not dotted sides, as two sides of our quadrilateral. So it can happen. So just to be clear here, there are scenarios where it is possible. Of course, if we connect these two other sides to a point on the circle, we now have a quadrilateral and we have that drawn inside a circle. Or this circle is now circumscribed around this quadrilateral there. But the reason I like thinking about it as starting with the triangle is that it helps us understand that this is really a special scenario. Because what if that point was not on the circle? Of course, this could be inside. What if we have a quadrilateral that's like this? Then we definitely have a no. If we have it outside, so I could pull these sides way out here. And then, of course, again, the answer is no. Now, so this is a special scenario. It's special when we have a quadrilateral that can have a circle drawn around it, that can be circumscribed around that quadrilateral there. So this is a special scenario, and oftentimes in mathematics, when we have a special scenario, we of course have a name for it as well. So let me draw back this at least one example where it does work, and we call this a cyclic quadrilateral. When it is possible, it's not always possible, but it can be possible sometimes. And when it is possible, we say we have a cyclic quadrilateral like this. Again, we don't have this terminology for triangles because it's always possible. You could say every triangle is a cyclic quadrilateral. So that would make sense still. This is used, cyclic is used for other shapes. If you have a pentagon, you could have a cyclic pentagon. But cyclic quadrilaterals, being one step up from triangles, are more of the famous examples to think about. And there's a lot of nice properties that we're going to talk about today as well. Now, what we aren't going to talk about is how to create the circle, or where does the circle come from, and things like that. Now, one of the reasons for that is that if you have a cyclic quadrilateral, so for example, suppose we have this cyclic quadrilateral, meaning we don't know the circle around it. Why are we not going to talk much about how the circle, where the circle comes from, how could you get the circumradius, all of those things? Well, you could always just look at the triangle. So take your pick. You could pick any triangle in that quadrilateral. Maybe you pick this triangle that we started with in our example, but you could have very well picked this triangle here. You just pick two of the sides, connect them on the other side, and then everything we did in the circumcircle video talking about triangles, stuff like that, that can be applied, and that's going to work for this quadrilateral as well. So that's why the focus is not on where the circle comes from, because you can use everything we know for triangles for that. But it's more going to be focused on when is this possible. We want to answer the question in a sense, when can we have a circle drawn around this quadrilateral? Now, we're not going to do the full proofs, but we want to start thinking about things like this a little bit. So, we're going to focus to start on angles. And I'm going to talk a little bit more about this, go a little bit farther than exactly what we have on this page here. But this first question, in a sense, is asking what can we say about angle ADB? So we have this angle here, ADB, and we want to compare that to angle ACB in this case. Now, let's do this a little bit slowly as it's our first one, but this is pretty straightforward there. Remember, if we're measuring angles in terms of a circle, so if we talk about angle ADB here, how do we measure that angle? Or how does it relate to arcs in the circle or things like that there? Well, it's 1/2 the measure of arc AB. So this isn't the angle there, but we have the arc AB in this case. And it's pretty easy to see that we can actually write this same thing for ACB. So in angle ACB, we also have this fact. This is also 1/2 arc AB in this case, since these are both inscribed angles, and that means that those angles are equal to each other. They share that same arc, and so this is what tells us that actually angle ADB is equal to angle ACB. So we can say that these angles are equal in this case. You typically wouldn't even show all of this work there. We would say words like they share the same arc. They're two inscribed angles with the same arc, AB, so their values are equal in that case too. Now, just taking this a slight bit further here, we're not going to do the full proof of this, but we will state this later. Notice as well if this was not a cyclic quadrilateral. So pretend for a moment that we were moving point C. What would happen if point C got moved outside of the circle, or if C got moved inside of the circle there? Notice that would make the angle smaller or bigger, right? If we have an angle inside the circle, it's going to be larger than that inscribed angle. If it's outside, it's going to be smaller. So in fact here, it has to work out perfectly, and it only works out perfectly so that these two angles are equal if they're both on the circle. So I'm not going to say too much more about that now, but this comes up as a fact later, and this is going to be true for the next slide and things like that as well. So we can keep that in mind, that this question is really a little bit more about more than us saying they're equal. Not only are they equal, but they're exactly equal when they're both on the circle. So if we don't have a cyclic quadrilateral, things break down as well. Now let's do something similar with other angles in this case. So what can we say about angle A and angle C in this cyclic quadrilateral. So now again, we have two angles in this case. So we're looking in this example at angle A and angle C in this case. So we have our two angles there. Now, let's be a little careful with notation and things like this as well. So we can write and start out with exact same equations in a sense. So angle A is, of course, angle BAD. So this is angle BAD, but just in that quadrilateral, we can call it angle A. That's 1/2 the arc BD. But let me just call it, for clarity, BCD in this case. So why am I calling it BCD? Well, this is a little bit of a spoilers, but we'll see in a second that we have this portion of the circle there. And I'm just including the C so that it's clear that we are that portion of the arc BD in this case. Now, why is that important? Well, what if we do the same thing for angle C? You could say this is the same arc, but angle C is, and again, just for clarity, let me call this arc DAB. So this time, if we want to continue going around clockwise, we would say we're going from D to B, but just to clarify this, we are saying it's the arc BD that contains A in this scenario. Now, what is the key here in this case? Well, the key is that those two arcs make a full circle. So the two arcs actually are a full circle in this case. So of course BCD, arc BCD plus arc DAB is a full circle. So that is 360 degrees in this case. So we have a full circle there. And that's giving us the punchline here that our two angles actually just add up to 180 degrees. So angle A plus angle C. If you wanted to show the work, they add up to 1/2 of a full circle. So they add up to 180 degrees in this scenario. Now, I didn't mention this on the previous part 1 of this angles thing, but it should be pretty obvious, and hopefully it's clear to everyone, that of course this is nothing special about A and C. The labeling there doesn't matter. This is a statement about two opposite angles in this cyclic quadrilateral. So the same thing is true for angle B plus angle D. On the previous slide, that's true for any of the times they share the same arc there. So for example, angle BAC is equal to angle BDC as well. So these things are true for a lot of the different cases in that scenario. Okay. So this is now another characterization in terms of angles. And again, this gets messed up. If angle C is moved inside, if the point C is inside, that angle gets bigger. So the sum is going to be bigger than 180. If angle C is pushed outside, it's going to be smaller than 180. We have the statement there that it works perfectly when C is on the circle. So when we have a cyclic quadrilateral, that's the only time things work out nice in that case. Now, before we end with a summary of these properties, let's just do a couple of quick examples here in terms of what are some common shapes that we have for cyclic quadrilaterals. This is a little less common than you may think. So a pretty obvious one that works is a square. So definitely here, if I have a square has angles that add up to 180 degrees. 90 plus 90 is 180 degrees. So we definitely have squares that will work in this case. Hopefully it's pretty obvious from this picture too, or from what I just said, especially about the 90-degree thing too, that in fact rectangles will work as well. So not only do squares work, We could also just have a rectangle in general. Any rectangle in general will also work there. So rectangles are going to be okay as well. Now, what about some other shapes? Let's maybe have some non-examples. I'm not going to keep them on the board there. But for example, what if we try to draw like a parallelogram in this case? Well, a parallelogram, of course, if it's a rectangle, then it's going to work. But in general, a parallelogram is not going to work. Now, this picture might remind you of something. Well, what if we extend this other side here? What if we extend this side and then we have our situation like this here? So now we have a trapezoid. Now, this picture makes it seem like trapezoids will work. But we actually need to be a little bit careful with that there. So this is one thing you want to be careful with when you're drawing these examples. If we're just drawing it in the circle anyway, we might think we're not assuming something. We have a trapezoid like this, then it works in this case. But remember, a real trapezoid could be moved off center. So what if we have this off-center trapezoid like this? That's a little bit more clear that even if I drew a different circle, that's not going to work. That's not necessarily going to work. One way to think about it again is the angles. Do these two angles, say this is a 90-degree angle and this angle, those two angles do not add up to 180 degrees. That would be bigger than 180 degrees, so it's not going to work in this case. So be careful with the moving stuff around. In fact, however, we can kind of see what is needed in this case. If we have an isosceles trapezoid, then it's going to work. So if we have the two sides here that are equal in that case, if we have two equal sides, if it's a centered trapezoid like that there, then it's going to be fine. And in terms of the nice shapes, right, squares, rectangles, we said parallelograms in general don't work. You would have to be a rectangle for that to work. Trapezoids don't work, but if it's an isosceles trapezoid, that is okay there. Okay. Now let's just end with a summary of what we did, a little bit extra, and just talk about the different characterizations of a cyclic quadrilateral. And as I mentioned, these things work in both directions. So to summarize some of the stuff we've done, ABCD is a cyclic quadrilateral if and only if angle ADB equals angle ACD. Or sorry, ACB. So for example, these two angles have to be equal there. Of course, that's an etc. because as I mentioned, any angles that share an arc, so this angle and this angle have to be the same. And if you have a quadrilateral with that property, if we know that those two angles are equal, then it has to be a cyclic quadrilateral. That's the if and only if part of this statement. The same thing is true with the opposite angles. So if we have there our opposite angles in this case. So if we have angle A plus angle C is 180 or B plus D is 180, then we know all of these other things are true. It's a cyclic quadrilateral, so these shared arc angles are the same, things like that as well. Last thing I want to mention is you can go back and look at the video for this. It's slightly different focus in an earlier Thursday tidbit, but we also have things like power of a point. In fact, this is an if and only if statement too. So we did this for quadrilaterals in a circle, remember, in previous cases. And then in this case, AE times CE equals BE times DE that way as well. So when we have these intersections, this is going to be true as well. So that is all some great things that we can know about cyclic quadrilaterals in this case. That's it for this video. So if you liked this, please like, subscribe, follow us, and check back each Thursday for a new math tidbit. And if you're looking for some extra resources, I recommend ziml.areteem.org and hope you join the community there at the Zoom International Math League. Goodbye, everyone.